Good morning, everyone. Thanks for inviting me to Coogee. I'm very happy to be here and to talk to you about some of my results on code switching for measurement-free quantum computing. So in the end, our overall, what we want to implement some universal quantum algorithm. And for this, we need several building blocks. On the one hand, to make sure that we can suppress overall error rates, and on the other hand, to implement arbitrary computations on our qubits. And the first is addressed by quantum error correction, which we've heard a lot about already this week. And the idea is to encode information on multiple qubits, and there are different ways of encoding information in, for example, topological degrees of freedom, and many methods of extracting stabilizer information that we can then use to correct errors on physical qubits. The second condition that we need is, so we want to implement arbitrary computations on these encoded protected qubits. And one way of implementing these is to use transversal circuit designs. So in these transversal circuit designs, we essentially just apply local unitaries to make sure that errors do not spread uncontrollably within an encoded block of qubits. So for example, here, this gate is a transversal logical Hadamard gate, for example, on the 2D color code, which I will talk about later on. And here, essentially, the number of errors before applying the gate is the same as the number of errors after applying it for a fault-free gate. But there's the no-go theorem by Easton and Knill that states that no quantum error correcting code exists that has a universal transversal encoded gate set. And we need a universal gate set to approximate arbitrary computations efficiently. And one typically uses these two methods of magic state injection that we've just heard about in the context of magic state cultivation. But today I will talk about code switching, which is sort of an alternative approach of realizing a fault-tolerant universal gate set. So I'll start by first talking about the general procedure. So how can we implement code switching protocols? Then I'll talk a bit about some conditions that have to be fulfilled to construct fault-tolerant protocols. And then in the second half of my talk, I will talk about how we can use code switching as a sort of deterministic way to implement measurement-free quantum computing that does not rely on mid-circuit measurements or feed-forward operations. Okay, so this is basically restating the Easton and Knill theorem. So let's say we have some code A that has a transversal Hadamard and a CNOT gate. This code will not have transversal T gate. So the idea is to take a second code B that has a complementary set of natively transversal gates. So here we'll choose a code that has a transversal T gate and maybe a CNOT, but then it does not have a transversal Hadamard gate. And the idea is now to, for example, start in code A and then transfer the encoded information to code B, apply the missing gate, and then switch back. And in this way, access the full fault-tolerant universal gate set. So if we now have some algorithm that we want to implement, we can simply shift this to the logical level, where now each gate is only applied in the regime with a respective transversal gate implementation. So for example, here, we'll start in code B, apply the fault-tolerant transversal T gate. But then in order to be able to apply the Hadamard gate transversal, you first have to switch to code A. So how can we do that? A convenient choice for our code A and B are color codes, because, for the following reasons. So here you can see a two-dimensional triangular color code, and stabilizers are defined symmetrically on each plaquette. So we define X and Z stabilizers on all of these colored plaquettes. So this code is self-dual, which means that we get a transversal Hadamard gate. And since this is CSS, we also have a transversal CNOT gate. In the following, so for the purpose of this talk, I will only talk about the smallest code instances, so distance 3 codes. And the smallest instance of this 2D color code is this Steen code that we've also just heard about. And here we have the transversal Hadamard and the CNOT. So if we now go to 3 dimensions, the smallest instance is this 15-qubit tetrahedral code. And now we not only have these 2-dimensional plaquettes, but we have 3-dimensional units, which we call the cells, and we have 2-dimensional units, so for example, interfaces between cells. And we now define X stabilizers on the volumes. So we have red, blue, green, and yellow. And the Z stabilizers we define on these 2-dimensional plaquettes. So we have 3 within this tetrahedral structure, then another 3, and 4 on the boundary. So this is not self-dual anymore, so we don't have a transversal Hadamard gate, but we can now implement a transversal T gate, as we've seen also yesterday. By simply applying physical T and T-DEC operations, we can implement a logical T gate. So this is basically our choice for our two codes with complementary gate sets. And I'll now talk about how we can transfer encoded information between these two codes. So one approach we've briefly seen yesterday in a talk where presented as basically the steam type approach, where we do transversal gates to another logical qubit. This is not what I'll do, so this will be slightly different. So I first talk about how to switch from this tetrahedral code to the steam code and discuss an example to make this more clear. Okay, so when I talk about the involved qubits, we're always talking about the same set of qubits. So we always have 15 qubits, and in the regime on the right, the information is encoded on this one side of this tetrahedral structure, which is our steam code. The remaining 8 qubits are always present, but in that regime, they don't encode any information, but are just in a specific state. And as I said, so on the left in the tetrahedron, a state is a +1 eigenstate of these x volumes, while on the right, our code state is a +1 eigenstate of the x faces. So to switch from one code to another, the first thing we do is we measure the stabilizers of the target code, which are not fulfilled initially. And this is just a random projection onto a +or -1 eigenstate of these x faces. So we get a random outcome in this case. Then in the second step, we have to apply an operation that on the one hand preserves the logical information, because we don't want to change that, but also on the other hand fixes the state into the desired target code space, because we want to change our encoding essentially. And this we can do by applying so-called gauge operators, which in this case are just stabilizers of our initial code. So let's look at an example. So again, switching from the tetrahedron to the steam code. First step is measuring the target stabilizers, which are not fulfilled. And this is a random projection. So for example, we could get this outcome of 1, 0, 0. So in normal quantum error correction, we would now assume, okay, there's an error, for example, here on this top qubit and correct it, but we can't do that because that changes the logical information. So what we do instead is we apply one of the gauge operators. So in this case, we'll apply this blue-green Z interface. And it overlaps at two sides with the green and blue plaquette. So we basically flip this twice. So we stay in a +1 eigenstate of these two plaquettes. And it overlaps only at a single side with the red one, so we fix the state into the correct target code space while maintaining the logical information. Okay, and this works completely analogously the other way around. So to switch from the steam code to the tetrahedron, we also just measure a set of stabilizers of the target code and apply gauge operators. But what about fault tolerance? So far, I have not talked about any errors that can happen in this procedure. So I'll try to, I will formulate 3 conditions that we have to keep in mind when constructing these protocols fault tolerantly. So the first is that switching should be independent of the specific input state. So let's look again at switching from the tetrahedron to the steam code and assume everything works perfectly. So everything is noise-free and our switch, no errors happen during the switching procedure. But there's now an initial error sitting on our logical qubit. For example, this way 3 error configuration would be correctable on the tetrahedral color code because we had these 10 independent Z stabilizers. So this is totally correctable initially. But if we now switch, nothing happens to this error configuration. So it's still there after switching. And on the steam code, this is directly a logical error, which is not correctable. So what we have to do is we have to insert a round of X error correction before switching to make sure that we can basically remove these dangerous error configurations before switching, such that we don't introduce a logical error even with a perfect switch. The second condition is that stabilizer measurements should not introduce uncorrectable errors. And this we've also seen yesterday already. So this is a standard circuit for measuring stabilizer fault tolerantly with this flag qubit approach. So here we have an auxiliary qubit that's coupled to the data qubits that support the stabilizer to be measured. And now, if an error occurs in the middle of the circuit, this propagates onto multiple data qubits, which could be dangerous. But in this case, it also propagates onto this flag qubit. And if we measure the flag in the end, we'll know that a potentially dangerous error has happened, and we can correct it with subsequent stabilizer measurements. So to fulfill the second condition, we can use the standard flag qubit schemes introduced in 2018. Then lastly, we have to make sure that errors on data qubits are distinguishable from the random projections. So what does that mean? Let's again look at an example to make this clear. So again, we start in this tetrahedron and want to switch to the Steen code. But now there's already a single error on one of the data qubits present. So here on the top qubit. And if in the original stabilizer measurement of these 3 X plaquettes, we would find the outcome 0, 0, 0, so we wouldn't do anything. We now get this inverted red plaquette, so we'll get 1, 0, 0. So in this case, we'll do the same thing as before. So we'll again apply this blue-green Z interface. But if we then look at the configuration that we effectively applied on the Steen code, we see that this is directly a logical error. So we have to make sure that we can identify these single errors on data qubits that would invert our stabilizer measurement outcomes to correct them or update our measured syndrome information. And this we can do with additional stabilizer measurements complementary to those that we already measure for switching. Okay, so now we have basically the tools that we need to implement fault-tolerant code switching protocols. And in our work, we look at different kinds of protocols and investigate performance, scalings, and thresholds. But what I want to talk about now is the experimental implementation of these protocols on an ion trap quantum processor. We had these 2 codes, but to implement this 3-dimensional color code, we need at least 17 qubits. So 50 data qubits and at least 2 physical auxiliary qubits to do these fault-tolerant stabilizer measurements. But at the time, at the University of Innsbruck, they only had 16 qubits, so we had to find a different version of this protocol. So I constructed some protocols using a slightly different version of this code, namely the 1012 code, which is the morphed tetrahedral color code. So here we effectively trade off the number of qubits that we need, but we also reduce the code distance. So now we only have a distance 2 code. But it inherits the fault-tolerant logical operations of its parent code. So we still have the fault-tolerant T gate, which in this case can be implemented by just applying physical T and T Decker gates and a control Z. So this is obviously not transversal anymore, but it's still fault-tolerant because any propagated single error that can happen in this scheme is detectable in the end, because basically these 3 qubits here participate in distinct stabilizers. So we can identify any propagated single error in this case. So it's not fully transversal, but still fault-tolerant in this detectable sense. So after constructing these protocols, we collaborated with the team in Innsbruck to implement these protocols on a trap ion quantum processor. So specifically, we look at these protocols. So we prepare a logical state. I will just point here on this 1012 code, and then insert the respective fault-tolerant gates that we can implement on each code. So we have Clifford gates, we have the fault-tolerant T gate, then we have this switching operation, and then the Hadamard on the 2-dimensional color code. And with these first 2 kind of operations, we can now prepare all of these states on the equator of the Bloch sphere, here in blue and green. And then we can add the Hadamard on the final Steen code, which basically rotates all of these states towards the polar circles of the Bloch sphere, like this. So here on the right, on the left, you can see basically this, the overall state fidelities that we obtain from logical state tomography for these different groups of states, and always compared experiment to simulation. And yeah, basically now we can prepare these logical states which are not natively reachable within a single quantum error correcting code. Then in the next step, we added a second logical qubit. So we again prepare a logical plus state on the 1012 code, switch to the Steen code, and then prepare a second logical qubit in another Steen code and apply a transversal CNOT gate, which basically gives us this logical Bell state. So here on the lower left, these black dashed boxes correspond to the ideal value, And, well, ideally, everything else would be blank, but of course there's noise. And now we can start inserting the fault-tolerant gates in this protocol. So T and Hadamard, which basically gives us these logical belt states with additional phases. Yeah, so basically to summarize this part, with these resources of up to 61 2-qubit gates and 2 mid-circuit measurements, we can run these minimal logical algorithms, including the full universal gate set. And also by now, these code switching protocols have been realized at Quantinuum and at Harvard for the full error-correcting tetrahedral color code. But what we can also see is that here the fidelities drop. So if we go from blue to orange, what we do is essentially we add a mid-circuit measurement while the number of 2-qubit gates is more or less the same. So in this case, really the mid-circuit measurements are extremely noisy and reduce the overall performance significantly. And this is not a problem specific to this one device or only to trapped ion devices. So measurements are fundamentally slow in trapped ion devices as well as neutral atom platforms. And also in other platforms, implementing this real-time feed-forward operations is difficult. And of course, there's a lot of effort going into improving these operations on an experimental side, but we decided to look at it from a theoretical algorithmic perspective and try to construct protocols that do not rely on these mid-circuit measurements with the hope of improving the overall performance, because we don't need these most noisy circuit components. So basically, in the next part of my talk, I will try to explain how these mid-circuit measurement-free protocols work in principle, and then explain how we can basically implement arbitrary computations without these measurements and scale this up to high distances, and in the end show some minimal, some small proof of concept experimental implementations of these protocols. Okay, so coming back to this algorithm picture from before, we now still have the same building blocks that we need to implement, but we have the problem that mid-circuit measurements are hard. And what we now did is we found a way to implement all of these building blocks without mid-circuit measurements or feed-forward operations. Okay, so in the past years, there have first been some proposals on measurement-free quantum error correction. And the idea is essentially the following. So we have some logical input state psi, and we prepare an auxiliary register in a suitable way to then perform the error correction as one unitary on this joint system, fully coherently, without any measurements or feed-forward operations. And in the end, we'll discard the auxiliary register to basically remove the entropy from the system. So here in this case, sorry, I don't. The top button, yeah, sorry. So here, on this state, we basically removed all the physical errors that we can remove with this kind of error correction. But this was limited to small distance codes because this essentially encodes a lookup table. So this is not natively scalable to high distances. And also, it was not clear how to implement logical operations in this measurement-free framework. So what we did then, we basically follow a similar approach. So again, we'll have some input state psi, and we want to perform some logical operation on this. And this is done by preparing, again, an auxiliary register, performing unitary operations on this joint system, and then discarding the auxiliary register in the end. And the idea is basically based on combining code switching and concatenation to then scale up. And shortly after, there was also a second work basically following similar ideas on combining gauge fixing and concatenation to achieve scaling in this measurement-free setting. Okay, so I will try to explain how to, what the circuit would look like on a high level, and also show specific circuit construction, to show how it really looks. So again, we'll look at switching from this tetrahedron to the Stein code. And the first step is to prepare the auxiliary register. So in this case, we prepare a logical Stein code instance that we can then use to map out the desired stabilizer information. So we, in the second step, apply a kind of transversal CNOT gate, which basically maps the information about the stabilizers on my data block onto this logical auxiliary register. Then we'll copy the syndrome onto physical auxiliary qubits. So these physical qubits basically then carry the syndrome information. So they'll be in the state 101 or so, basically corresponding to the syndrome that we extracted. So in the next step, we also have to use some information about the bulk stabilizer. So this yellow cell, this is what I call the bulk. And this is essentially the condition 3 from before. So this has to be done to identify errors on data qubits that would potentially lead to a logical error on the target code. So basically, all qubits have to participate in this measurement-free code switching gadget. Then, after extracting all the information that we need onto physical qubits, we basically have a syndrome, and we have to update our syndrome information if some potentially dangerous error on a data qubit has been detected or stored. It hasn't been detected technically, but yeah, this information is carried in these physical qubits. So here we'll need some kind of Toffoli gate operation to update our syndrome information, and this will be important later on. Then we apply our coherent feedback operation. And lastly, we have to reset the auxiliary system and basically repeat the previous steps to then finally apply the second part of our coherent feedback operation. So how does this actually look? So just to give an impression of this is the full circuit that we would need to implement this code switching gadget for switching without measurements from the tetrahedron to the steam code. So here, in the first part, here, this yellow box is this transversal CNOT. Then we store the syndrome information here on these physical qubits on the lower 3 lines. This top part is basically doing the same thing, so copying syndrome information onto physical qubits. Then in green, we basically update our syndrome information if a potentially dangerous error has occurred on one of the data qubits. And lastly, we apply our coherent feedback here, which is just a bunch of control Z gates in this case. So yeah, here I included reset operations, but in principle, yeah, you can reuse qubits, or you can use fresh auxiliary qubits, so that doesn't matter. So it's basically these 2 steps. So first, extracting the stabilizer information, and the second part is performing the coherent feedback to basically implement your gauge operator to switch. And importantly here, we need these Toffoli gates to achieve fault tolerance. That's the key takeaway here. And again, this works similarly for the inverse direction. So we can also switch without measurements from the steam code to the full tetrahedral code. In that case, we will need different kinds of logical auxiliary qubits, but the idea is the same. So yeah, basically following a similar approach. And we'll need up to 35 qubits in total to implement the full switching scheme. So again, in this algorithm picture, we can now think about scaling up. So what I showed so far was only for distance 3 codes. I only talked about the smallest instances of 2 and 3D color codes. But in the end, we want to go to high distance codes. So we now basically have these building blocks, so we can implement measurement-free quantum error correction for the distance 3 code. We have the Hadamard and the CNOT for the 2D color code. These are transversal anyways, so they don't include any measurements or so. Natively. And we now have this measurement-free switching operation, which gives us access to the logical T-gate in a fault-tolerant way. And now we concatenate. So each physical qubit that made up a logical 2D color code instance is now again a logical qubit. And the transversal gates, they straightforwardly generalize because every previously physical gate is just another transversal gate. So this is just a bunch of physical operations. But the error correction, as well as the switch, included these multi-qubit control gates. So we had these Toffoli gates. And these are now logical Toffoli gates. And if I look at the decomposition of a Toffoli gate here, this again includes a full logical universal gate set. But we can implement this, so because we have the switching gadget. So we simply insert our switch in this decomposition, which gives us access to the logical Toffoli gate. And this means that we can now implement the error correction scheme in a concatenated setting, as well as the switching operation, because we now have access to a measurement-free logical universal gate set. So yeah, in our work, we ran many simulations to investigate the performance. So for example, here you can see the results from circuit level noise simulations for switching in both directions. So first, for the non-fault-tolerant scheme, here in blue and orange, giving this linear scaling, and then for the full fault-tolerant scheme in green and blue, where we get this quadratic scaling. So the dashed gray lines correspond to the estimated polynomial. So we counted the number of error configurations that lead to a logical failure. And this basically corresponds to the number of wave 2 falls that can happen within any position of your circuit. And this gives you an estimate of your overall performance. And these align, basically verifying that the protocols are indeed fault tolerant. And then there's the question of, is it worth it? Should we do measurement-free or measurement-based protocols? So we did some more simulations. So here you can see basically a 2-parameter noise model. So we have the gate errors, the standard scheme for circuit level noise simulations. On every circuit component, there is an error happening with a probability p. And we introduce a second noise parameter, which corresponds to the error on idling qubits during measurements. And this you have typically dephasing during these long measurements, for example, on trapped ion setups or neutral atom platforms. And we looked at this protocol of implementing a logical Hadamard operation on the 15-qubit tetrahedral color code. So this includes basically switching back and forth. And we compare the measurement-based code switching protocol with the measurement-free code switching protocol. And essentially, red means that measurement-based outperforms measurement-free, and green indicates that measurement-free outperforms measurement-based. And these blobs that you can see basically correspond to current parameters on trapped ion and neutral atom devices. And most of these lie within the green region, indicating that measurement-free can be advantageous. So I want to emphasize that this is a rough estimate. So this is a very simplified noise model, and in reality, you of course have different noise parameters for different kinds of components. And also that's a question of what do you compare to. But yeah, this I would say implicates that measurement-free can be advantageous in certain settings. Okay, to summarize this part, basically we have these code switching protocols that we can use to implement a fault-tolerant universal gate set. And we can concatenate the scheme to gain access to, in principle, arbitrary distance codes that we can then use to implement these measurement-free protocols. And so far, I assumed all-to-all connectivity, which is basically, is convenient for trapped ion and neutral atom platforms where we have access to all-to-all connectivity. But also on these platforms, you have especially slow measurements as compared to others, making them basically ideal candidates for these measurement-free protocols. So we did some experimental proof of principle demonstrations, first for logical state teleportation, as well as Grover search on an 832 code. And I will show some of the results for our Grover search experiment. So the first step was basically constructing, again, a measurement-free universal gate set for this code. And since in this code, as we've heard yesterday already, we basically natively have this transversal control Z gates, as well as CNOT gates that can be implemented by swapping pairs of qubits. And here I basically constructed a measurement-free protocol for implementing a logical Hadamard gate on one of the encoded qubits in this 832 code. And then we can use this to implement a small-scale logical algorithm. And specifically, we looked at Grover search, which is the search for an element in an unsorted database. And here on the right, you can see the circuit that essentially implements a two-solution phased oracle in a search space of 8 bits. So in this case, we have 8 logical bits in that sense, so 3 logical qubits. So we take the circuit and basically recompile it into our available measurement-free gate set. And this is what we find. So here you can see the outcome probabilities for each of the 8 possible outcome states. And again, we can compare experiment and simulation, and green indicates this is one of the solution states, and red indicates this is not one of the solution states. So ideally, all the red should vanish, which is of course not the case because, yeah, the circuit is noisy. So we can clearly identify the solution states because we get much higher probabilities. And we find an overall success probability of 40%. And we are currently extending this to larger codes, which also give access to full error-correcting versions of these protocols. And I'm fast, so this is already my summary slide. So in the first half of my talk, I talked about code switching protocols and how to implement these in a fault-tolerant setting. So these conditions that have to be fulfilled to ensure that we can maintain fault tolerance. And I talked about the experimental implementation on a trapped ion device. And in the second part, I presented this toolbox that gives access to measurement-free universal quantum computing from principal arbitrary distance codes. And I very briefly showed this experimental proof of principle demonstration for Grover search on an 832 code. Yeah, and with this, I'd like to thank you for your attention, and I'm happy to take questions.
Thanks very much. It's really great to see. So I'm particularly interested in sort of the measurement-free quantum computing thing, which is really good to see that you can do large-scale fault tolerance. So I suppose my question is, have you thought about the extent, so if I'm really doing this on a large scale, I need to replace my physical qubit measurements with physical qubit state preparations. So I need to either reset ancillars or re-prepare new ancillars.
Yes.
And in a lot of qubit architectures, the physics of the state reset is quite similar to the physics of the measurement. And so it's also kind of slow. And I'm just wondering the extent to which you've sort of thought of that. Like, I don't know in the ion traps what it's like. Let's say in IBM devices, they literally do resets through measurements.
Yeah.
So I'm just wondering, what are the possibilities? It seems like there's a lot of possibilities to try and, use something like that you can do offline to get around the fact that it's slow. But fundamentally, I'm going to need to be doing these slow, noisy reset operations instead of slow, noisy measurements. And I was just wondering if you thought about that, what thoughts you might have about doing that.
Yeah, we did implement these reset operations, and I also simulated them. So specific for trapped ion devices, you can reset a qubit with a measurement, but physically you need to scatter much less photons. So in a measurement, you have to scatter like thousands of photons and detect it with a camera. And for reset, in principle, you only need to scatter like a few photons. And also in practice, this on this device is much faster than actual measurement. Yeah.
Thanks for the great talk. I'm sort of struck by, again, the prominence that the Toffoli plays in these measurement-free schemes. And wondering if that is sort of really fundamental to these schemes. Like, should we be focusing on, when we're looking for potential codes that would allow us to do code switching and a universal gate set, focusing in specifically on codes or code pairs where we're going to be able to do logical Toffolies natively or simply in some fault-tolerant way. You showed the 3D surface code, for example. It's good, but we want to look for others. We're so used to with CSS codes having that native CNOT, and should we further focus down to codes where we also have a matching code for code switching where there's a native Toffoli? Is that a really good requirement, or is the Toffoli just sort of an artifact of this construction and you can do it with any non-Clifford gate?
So I emphasize it that much because basically this was the key building block that we needed to scale up. If one had a natively transversal Toffoli gate, this would definitely speed this up and make it a lot easier. I think there's not been like a ton of research in this direction. So maybe there are codes where you could then get around this. But I think especially for the error correction, measurement-free error correction, so any approach there is so far basically relies on these multi-qubit control gates, because basically you hard code your lookup table. And currently I would not see a way around this for measurement-free error correction. But for code switching and this logical non-cipher gate, there might be a way, yeah. But I don't know specifics.
Thanks for the great talk. I'm interested in, like, have you thought about, like, what's the time overhead if you, like, further concatenate, like, like a multi-layers? Because I assume that you would use, like, switch, like, even the smaller codes all the time?
Yeah, we did some, I think we mostly looked at the logical error rates in this concatenated setting. We did not do an elaborate time over analysis. But I think in this concatenated setting, you can in principle parallelize a lot. So I think it would be okay, but I don't have numbers.
And then I guess like a similar question, or like something I fully understand is, do you need to fault-tolerantly prepare this decode in solid states?
Yes.
Oh, okay.
Yes. But you can do that measurement-free with basically you. I think we've seen the flag circuit. So to do it measurement-free, you don't extract a single logical value, but a complementary stabilizer, and then do some feedback. So yeah.
I had a question as well. So I don't understand trapped ions and neutral atoms as well, but I would think that, like, is there some leakage or data or qubit loss, sorry, that you usually would detect via measurements, and are you sort of suffering because you remove the measurements from the protocol?
So at least in this setup, leakage is not a big problem because they have huge coherence times. But I think what we should investigate more are coherent errors. Because if you do stabilizer measurements, you basically project and you get rid of these coherence of these coherent errors. And in this measurement-free setting, I think right now it's unclear if they would accumulate over time or if you have deep circuits or so. So I think, yeah, we have to investigate what about coherent errors.
I have a related question. So is the error model you use in all the simulations like just Pauli error model?
Yes.
But then wouldn't that not really be justified because usually the justification is you project it onto all the stabilizers?
Yeah, so we have a short discussion on this in our paper on this. So yeah, I think you should include coherent errors, but since you discard your auxiliary register in the end, there's some sort of projection there. That's the idea.
Okay, if we don't have further questions. Oh, sorry.
I'm just inspired by Dom's question. I mean, so a lot of us, you might imagine getting around coherent errors in the fault-tolerant setting by using something like randomized compiling. So like you kind of randomize the Pauli frame to. So do you know how to do that in this measurement-based setting, like something like a random Pauli frame, or is that like not really possible?
I would say it should be possible, but no one has looked at it as far as I know. So there's not been a lot of research on measurement-free.
No.
So it has been done.
Yeah, the thing that worries me about the measurement-free thing is the decoding of like large codes. Then we need like a huge property circuit. But have you looked at some codes they admit a local decoder, and this seems like maybe perfect for this kind of thing.
Yeah, this is something we are looking into at the moment. Yeah. So you need some locality, but yeah, I think. Yeah.
Like fully Torah code or something, you could decode it with like an automaton.
Yeah.